cells, direct liquid fuel cells, and microbial fuel cells. We explore advanced technologies in solid-state hydrogen storage and liquid organic hydrogen carriers. Safety considerations and the development of hydrogen and fuel cell safety technical codes are also integral parts of our work. Driving innovation and pushing the boundaries of fuel cell and hydrogen technology. Groundbreaking collaborations with esteemed industry partners. Obtain more than 50 million ringgit in research grants. Our institute proudly offers 3 programs: research-oriented, Masters of Science, Doctoral of Philosophy programs, Master of Science in Low Carbon and Hydrogen Technology, and Micro-Credential. Our alumni are a diverse group of individuals who cover the globe, leading education, reshaping industry landscape toward a model of self-leadership, creativity, and innovation. As a leading institution in fuel cell and hydrogen research, we have forged strong collaborations with top-tier universities across the globe. Through these collaborations, our students and researchers gain valuable international exposure, enhancing their academic and professional growth while contributing to the global scientific community. Join us at CellFuel and embark on a transformative educational journey that will empower you to excel and make a lasting impact on our sustainable world.
Selamat pagi Bapak Ibu peserta sekalian. Selamat datang di Zoom webinar kami. Kami informasikan bahwa webinar akan segera dimulai. Kami mohon kepada seluruh peserta untuk mempersiapkan diri dan menonaktifkan mikrofon selama acara berlangsung demi kelancaran jalannya acara. Dan kami mohon juga kesediaan Bapak Ibu untuk menggunakan virtual background yang sudah kami bagikan di kolom chat. Terima kasih atas perhatian Bapak Ibu. Acara akan segera kita mulai dalam 5 menit lagi.
uncontrolled carbon emissions contribute to global climate change crisis. Global climate change has devastating effects on ecosystems. The answer lies in hydrogen, a powerful solution that holds the key to our sustainable future. But how? Hydrogen is a game changer. And at the forefront of Malaysia's hydrogen revolution stands the Fuel Cell Institute of Universiti Kebangsaan Malaysia. The Fuel Cell Institute, also known as CellFuel, is a premier national research centre at UKM. Established on July 1st, 2006, our goal is to become a centre of excellence for fuel cell and hydrogen technology around the world. Consistent with government goals of expanding opportunities for clean energy sources. The shift from a carbon economy to a hydrogen economy holds the key to a brighter, cleaner future for all. At CellFuel, our research covers the entire hydrogen economy value chain. We delve into diverse areas ranging from hydrocarbon production, utilizing solar and renewable electricity, sustainable hydrocarbon thermal chemical processes, and biological hydrogen production through fermentation and microbial electrolysis cells. Our research also encompasses the utilization of hydrogen in various fuel cell types, including proton exchange membrane fuel cells, solid oxide fuel cells, direct liquid fuel cells, and microbial fuel cells. We explore advanced technologies in solid-state hydrogen storage and liquid organic hydrogen carriers. Safety considerations and the development of hydrogen and fuel cell safety technical codes are also integral parts of our work. Driving innovation and pushing the boundaries of fuel cell and hydrogen technology. Groundbreaking collaborations with esteemed industry partners. Obtain more than 50 million ringgit in research grants. Our institute proudly offers 3 programs: research-oriented, Masters of Science, Doctoral of Philosophy programs, Master of Science in Low Carbon and Hydrogen Technology, and Micro-Credential. Our alumni are a diverse group of individuals who cover the globe, leading education, reshaping industry landscape toward a model of self-leadership, creativity, and innovation. As a leading institution in fuel cell and hydrogen research, we have forged strong collaborations with top-tier universities across the globe. Through these collaborations, our students and researchers gain valuable international exposure, enhancing their academic and professional growth while contributing to the global scientific community.
Baiklah, Bapak Ibu, acara kita mulai. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat pagi dan salam sejahtera bagi kita semua. Yang kami hormati, Profesor Dr. Enia Listiani Dewi, Direktur Jenderal Energi Baru Terbarukan dan Konservasi Energi atau EBTKE, Kementerian ESDM, sekaligus Presiden Indonesia Fuel Cell and Hydrogen Energy atau IFHE, Profesor Dr. Jarod Raharjo, Ketua Kelompok Riset Material Fuel Cell dan Hidrogen, Badan Riset dan Inovasi Nasional atau BRIN, sekaligus Sekretaris Jenderal IFHE. Dr. Rian Ahmad Budiman, peneliti dari Pusat Riset Material Energi BRIN, Associate Profesor Dr. Muhammad Sahbudin Mastar, Deputy Director Fuel Cell Institute, Universiti Kebangsaan Malaysia. Dr. Nur Aziana Aliteh, Engineer of Hydrogen Energy Solution Section dari Hyoki Corporation, Japan, serta hadirin seluruh peserta webinar yang berbahagia. Pertama-tama, marilah kita panjatkan puji syukur kehadirat Allah Subhanahu wa Ta'ala, Tuhan yang Maha Esa, karena atas rahmat dan karunia-Nya kita dapat hadir dalam acara webinar ini dalam keadaan sehat walafiat. Kami ucapkan selamat datang di acara webinar e-talk yang ke-14, webinar series on Clean Energy and Advanced Materials, yang diselenggarakan oleh Indonesia Fuel Cell and Hydrogen Energy atau IFHE dan Kelompok Riset Material Fuel Cell dan Hidrogen Badan Riset dan Inovasi Nasional. Terima kasih kami ucapkan kepada Bapak Ibu seluruh peserta yang telah berkenan hadir pada acara webinar hari ini. Kami informasikan bahwa webinar kali ini disponsori oleh PT Hyoki Electric Instrument, PT ITS Science Indonesia, dan PT PLN Nusa Daya. Terima kasih kami ucapkan kepada seluruh sponsor. Baik Bapak Ibu dan hadirin yang kami hormati, sebelum acara dimulai, izinkan saya selaku pembawa acara untuk membacakan susunan acara pada hari ini, yaitu sebagai berikut. Acara pertama pembukaan, selanjutnya menyanyikan lagu Indonesia Raya, sambutan oleh Profesor Dr. Enia Listiani Dewi, foto bersama, kemudian sesi utama webinar yaitu presentasi dan diskusi yang akan dipandu oleh Dr. Rian Ahmad Budiman. Setelah itu penyerahan sertifikat, pengumuman door prize, dan terakhir penutup. Baiklah Bapak Ibu dan hadirin sekalian, marilah kita mulai acara ini dengan membaca basmalah bagi yang beragama Islam. Bismillahirrahmanirrahim. Semoga acara dapat berjalan dengan lancar. Baik Bapak Ibu dan hadirin yang kami hormati, acara selanjutnya yaitu menyanyikan lagu Indonesia Raya. Hadirin dimohon untuk mengambil sikap sempurna, dan marilah kita bersama-sama menyanyikan lagu Indonesia Raya.
Indonesia,
Baik, terima kasih. Bapak, Ibu, dan hadirin sekalian, acara berikutnya adalah sambutan yang akan disampaikan oleh Profesor Dr. Enia Listiani Dewi, Direktur Jenderal EBTKE Kementerian ESDM, sekaligus Presiden IFHE. Kepada Ibu Prof. Enia, dengan hormat kami persilahkan.
Hello, good morning, everyone, distinguished ladies and gentlemen. Happy to see you again in the Indonesia Fuel Cell and Hydrogen Energy program to have a study and webinar today. I'm happy to be with you, but I cannot join you in person. But I say that this is incredible moment that we will share about the knowledge regarding to the hydrogen and ammonia development. So as we know that Indonesia Fuel Cell and Hydrogen Energy (IFE) is making a lot project to contribute the development of the knowledge and also developing the industry that work on the hydrogen and ammonia. So national program, we have already launched the National Hydrogen and Ammonia Roadmap that already have a specific action plan regarding to our national energy planning until 2060. So in this national program roadmap, we have several action plans that must be followed by the industry because we addressing so much in the industry contribution, how they can make the action on the hydrogen and ammonia development. So here about that, we have a target on the next year is 190 ton per year of the green hydrogen production as already have been and our target. So if we talk about the 2060, it's about 11.7 million ton of hydrogen demand can create. So what is the problem right now? We must have the we have the unique ecosystem now in Indonesia. So we will have a unique ecosystem to develop, and then now regarding to the what we say step by step to make a forward to accelerating the green hydrogen action, we now encourage many people to understand about the hydrogen, how can use it in the energy sector, because we know hydrogen is a lot on the industrial sector, but in the next one for the energy. And regarding to the what we need right now is, of course, based on the technology, we need research and development, and addressing the research and development, we need more people to do the reverse engineering of the technology and to do the research to accelerating the how we can make the manufacturing industry to support the hydrogen and ammonia. So I think this discussion, this online discussion, this webinar discussion would address so much in the research and development, and we waiting for the new concept, new idea to create more on such as new materials or even the technology that we can address to produce the hydrogen. And we are happy to share to you about the hydrogen refilling station that already been two locations in Indonesia, and we are also have several groundbreaking like hydrogen and ammonia planning using the electrolyzer. So there is so much moving now in Indonesia. Thank you so much. Hope you enjoy the discussion. Thank you. Happy a good day.
Demikian tadi telah kita simak bersama sambutan dari Prof. Enia, Direktur Jenderal EBTKE Kementerian ESDM, sekaligus Presiden IFHE. Kepada Ibu Prof. Enia Listiani Dewi, kami ucapkan terima kasih atas sambutannya. Baik, Bapak Ibu dan hadirin sekalian, sebelum melanjutkan acara, marilah kita berfoto bersama terlebih dahulu untuk dokumentasi. Dimohon kepada seluruh peserta untuk menyalakan kamera dan tersenyum ke arah layar. Baik, mohon bantuan kepada panitia yang bertugas untuk mengambil foto. Saya hitung mulai dari halaman pertama. Saya hitung 3, 2, 1, smile. Oke. Halaman berikutnya. 3, 2, 1. Oke. Halaman berikutnya. 3, 2, 1. Next. Sudah? Oke. Baik, sudah semua foto diambil. Terima kasih kepada Bapak Ibu peserta sekalian dan panitia yang bertugas. Bapak Ibu dan hadirin yang berbahagia, kita memasuki acara inti webinar kita pada hari ini, yaitu sesi presentasi dan diskusi. Sebelum itu, perlu kami sampaikan bahwa akan ada door prize untuk 3 orang penanya terbaik di sesi diskusi nanti. Jadi, Bapak Ibu jangan lewatkan kesempatan untuk bertanya pada sesi diskusi. Kami informasikan juga Bapak Ibu yang terlempar keluar dari Zoom atau dan kesulitan untuk bergabung kembali, dapat bergabung melalui YouTube IFHE Official. Acara ini juga kami siarkan secara langsung via YouTube IFHE. Kami informasikan kepada Bapak Ibu dan hadirin sekalian, untuk link presensi akan di-share di kolom chat saat sesi tanya-jawab, dan kami mohon kesediaan Bapak Ibu untuk dapat mengisi daftar hadir. Untuk daftar hadir hanya dapat diisi 1 kali. Untuk itu, kami mengingatkan kembali Bapak Ibu untuk memastikan data-data yang diisikan telah sesuai karena akan digunakan untuk sertifikat peserta. Dan kami mengingatkan kembali kepada Bapak Ibu peserta yang baru bergabung via Zoom, dapat menggunakan virtual background yang telah kami sediakan. Demikian kami sampaikan, terima kasih. Bapak Ibu dan hadirin sekalian, untuk sesi presentasi dan diskusi atau tanya-jawab kali ini akan dipandu oleh Dr. Rian Ahmad Budiman dari Pusat Riset Material Energi BRIN. Izinkan saya bacakan profil singkat beliau. Dr. Rian Ahmad Budiman meraih gelar PhD dari Graduate School of Environmental Studies, Tohoku University, Jepang pada tahun 2015. Setelah itu, beliau bekerja di National Institute of Advanced Industrial Science and Technology atau AST di Tsukuba, Jepang hingga tahun 2022. Selanjutnya, beliau menjabat sebagai asisten profesor di Tohoku University hingga tahun 2025 dengan afiliasi ganda bersama BRIN. Saat ini, beliau aktif bekerja di BRIN dan tengah meneliti solid oxide cell sebagai sistem pembangkit listrik. Demikianlah tadi profil singkat Dr. Rian. Baiklah Bapak Ibu dan hadirin sekalian, selanjutnya izinkan saya menyerahkan jalannya acara kepada moderator. Kepada Dr. Rian, kami persilahkan untuk memandu acara.
Terima kasih atas perkenalannya. Baik, saya akan mulai memandu untuk webinar kali ini. Kita mempunyai 2 presenter dari Malaysia dan 1 dari Jepang. Sebelum itu, presentasi akan diberikan dalam bahasa Inggris dan question and answer atau Q&A, diskusi akan bisa diberikan dalam bahasa Indonesia atau Melayu. Mungkin juga ada pertanyaan dalam bahasa Inggris, itu juga lebih baik. Baik, sebelum mulai presentasi yang pertama, saya akan memperkenalkan dulu satu presenter yang pertama. So thank you very much for everyone come to this webinar. So I would like to introduce the first presenter from the University Kebangsaan Malaysia, Dr. Muhammad Shahabuddin Master. Dr. Muhammad Shahbuddin holds bachelor degree in biochemical engineering and master of science in chemical engineering from University Kebangsaan Malaysia. He earned his PhD in chemical engineering from Gunma University, Japan in 2010 with specialization in fuel cell technology. He is currently an associate professor in the Department of Chemical and Process Engineering, Faculty of Engineering and Built Environment, and an associate fellow at the Fuel Cell Institute, UKN. His research interests span a broad range of energy and sustainability topics, including fuel cells and hydrogen technologies, biomass, bioenergy, biogas purification, and engineering education. Dr. Shahbuddin has authored over hundreds of publications in peer-reviewed journals, books, and conference proceedings. He also holds several patents and has developed multiple product prototypes. His research has been supported by a diverse range of funding sources, including institutional, governmental, industrial, international grants, and consultation primarily focused on advancing fuel cell and hydrogen energy technologies. That is the biography of Associate Professor Dr. Muhammad Shahbuddin Master. Before start the presentation, I would like to remind for everyone to turn off your microphone and please stay until the last session, last the second presenter. So if you have any question, you can drop into the chat box in the Zoom here, or you can ask directly to Dr. Shahbuddin at the discussion session. So for Dr. Shahbuddin, would you mind to start your presentation?
Okay, thank you, Dr. Rian, for the nice introductions. So, Assalamualaikum and very good morning, Bapak-bapak, Ibu-ibu, dan para hadirin sekalian. Firstly, it is my truly honor to be here as one of the speaker for this webinar under this head. So, I will share my slide. Can you see my slide?
Yes, we can see your slide. Could you please increase your the volume of your speaker? So because it's quite low volume here.
Okay. More clear, Dr. Rian?
Little bit. Please increase the volume.
So as a given for the title for me, so I would like to give my little knowledge regarding on the title given. Low temperature electrolyzer for green hydrogen productions. Okay. So this is my content and outline for this slide. So first, I will introduce or give us some background on the hydrogen technologies. And then I will concentrate on the water electrolyzer technology. Basically, I will emphasize that on the low temperature electrolyzer, including the mechanisms and principles, materials, components, systems, which is balance of plant, the operations and performance, and also a little bit on the challenges and considerations, and also the future directions. And at the end, I will conclude my presentations. So as introductions, I think I believe that everyone aware on this part. So this is the current energy scenario or issues. Basically, at this moment, we rely on the fossil fuel, petroleums and natural gas and so on. So basically, it will increase in terms of the cost of energy due to the depletions of the fossil fuels. And also, this is basically the issues on the system efficiency, and also it will affect on the environmental impacts. So then, so basically, worlds need a future energy goal for the sustainable development. For that reasons, the United Nations have their own goal, which is called the Sustainable Development Goal, which is part of it is to have a new energy transitions, for example, renewables and alternative energy. So basically in renewables energy, we have about 6 to 7 category. So including the hydropower, wind energy, solar energy, biomass, geothermal, ocean energy, as well as the hydrogen energy. Hydrogen is one of the renewables energy resources. Then why hydrogen? Okay, when we look into the characteristics, there is a lot of excellence in terms of the characteristics, including the hydrogen is the simplest elements on Earth, and also the abundance is very huge, about 70% of the mass in the universe, and in terms of the energy density is quite high. And when we use or when we apply the hydrogens to the energy, for example, using the fuel cell as a power generation unit, so we can have only water as a byproduct and also the thermal. So, and this is the benefits of the hydrogen for the energy. For example, it can has a quick refueling times, environmental benefits, quite long-term vehicle operating costs, and also the economic benefits, and also the efficiency will be high compared to the internal combustion engine. And when we look into the applications, the hydrogen has a potentials in terms of the energies, infrastructure, storage, and resiliencies. And when you see in terms of the applications, we can say we can apply into the transportations and also the industrial. For example, we can use the hydrogen to produce the ammonia, for example. And for that reason, we can say that the hydrogen is versatile, zero emissions, and also efficient energy carrier. And when we look into the hydrogen production technology, so basically we have about 3 color. This is the common color. For example, we have the gray hydrogens, blue hydrogens, and green hydrogen. And basically, in reality, basically we have another several color code for the hydrogens, including the brown, gray, turquoise, blue, pinks, yellow, and green, which is, this is depend on what is the raw materials and what is the process, and at the end in terms of the efficiency. But by looking to this color, basically we can say that if we consider for the green hydrogen productions, so basically of course in terms of the waste, there will no waste, and of course in terms of the technology, basically it is refer towards on the electrolysis processes. So either the code color is yellow or green, and basically in terms of the environment, it is very environmental friendly because there is no waste. Okay. Okay, and this is in terms of the timeline for the hydrogen production methods. Okay, and we can divide into distributed and centralized hydrogen productions. Okay, and we can see that this is at the near terms, okay, mid-terms and long terms, and the technology basically are referring to the electrolysis technology as one of the potential technology to produce the hydrogen. So by looking to this technology, we can conclude that there is 2 kind of the technology for the electrolysis, either for the low temperature, which is use the alkaline electrolyzer, and then we have the PEM electrolyzer and also the AEM electrolyzer. This is considered as a low temperature, and for the high temperature, basically we have the solid oxide electrolyzer. And this is the characteristics or the types of the electrolyzer in more detail. For example, at the low temperature, as I mentioned before, we have the alkaline electrolyzer, and we have the anion exchange membrane electrolyzer, and also the PEMS electrolyzer. And this is the high temperature electrolyzer, as mentioned before. This is referred to the solid oxide electrolyzer. And for this topic, basically, I will more focus on the low temperature electrolysis. But in low temperature electrolysis, basically, as I mentioned, there is different types. For example, this is the alkaline based electrolyzer, which is alkaline electrolyzer, and have their difference in terms of the operations, directions, the advantage and disadvantage. And also, we have another polymer electrolyte membrane, which is the solid electrolyte, this is referred to the anion exchange membrane. Basically, the anion exchange membrane is slightly alkaline medium, while for the PEM electrolyzer, basically in acid medium electrolyzer. So, and when we see in terms of the difference in terms of the operating, for example, the charge carrier, the temperature, electrolytes, directions, the electrodes, all difference in terms of difference of types electrolyzer. And also when we see in terms of there is a several advantage and disadvantage depends on each electrolyzer. And also basically there is a difference in terms of the efficiency. So when you see here, for example, the alkalines, the efficiency can be up to only 70%. For the PEM electrolyzer, for example, can be up to 82%, while for the high temperature of the electrolyzer, maybe it can be up to 100%, which is depends on the systems. So in terms of the efficiency, basically we need to know what is the fundamental behind it. So basically, this is the thermodynamics of the electrochemistry for the electrolyzer, basically. So basically, either the medium is under liquid phase or the vapor phase. So basically, for the low temperature electrolyzer, basically we are referring to the liquid phase as a medium for the water. So basically, this is the amount of the energy for the liquid phase. Basically, we are referring to the high heating value, which is the amount is about 237 kilojoule per mole. While in vapor phase, basically this is basically referring to the solid oxide fuel cells. So basically, in terms of the energy values can be the value is 228 kilojoule per mole. This is referring to the low heating value. And then in terms of the performance, basically we are referring to the polarization curve. Basically, this is indicator to know what is the performance for the electrolyzer. For example, by looking to this polarization curve or this curve, so we can know exactly, or we can know roughly what is the efficiency for the each electrolyzer unit. Okay, so for example, as mentioned before, this is the, if we look into the HHV, high heating value, so we can have the power to produce for 1 kilogram of the hydrogen is about 39.4. While when we're referring to the low heating value, the amount of the energy required to produce 1 kilogram of hydrogen is about 33.3 kilowatt hour. And this is basically referring to the amount of the voltage for the single cells of the electrolyzer. For example, if we are referring to the HHV, so the voltage is about 1.48 for the one cells. While for the LHV, the voltage would be about 1.23 volts. And basically, by referring to the thermodynamic, then we can realize what is the correlations between the current, okay, and the hydrogen production. So basically, if we need to high hydrogen productions, so basically we need to put a very high current, and it will affect on the design. Basically, for example, the electrode size, we call it as a active area or MEA size. So basically, the area should be bigger if we need to have a very high hydrogen flow rates. And of course, when we see in terms of the energy requirement to produce the hydrogen production. So basically, we just simply multiply what is the current and also what is the voltage operate for example, for the one cells or for the multi-stack or for the systems. And then again, on the polarization curve, basically, this is the fundamental that we need to know. Basically, there is a three main category for the losses. For example, the most losses can happen is for the catalyst activities. This is due to the electrochemical reactions on the electrolyzer. So basically, there is several factors, including the catalyst types, the catalyst loadings and utilizations, and electrochemical active area and the stability of supports of the catalyst. And the second part, this is referred to this medium current density. For example, this is referring to the off-peak resistance, including the membrane's criteria or properties, the conductivities, and the membrane thickness, and also including the bipolar plate itself. Okay, and also we have another losses, which is this is referring to the mass transport, including the gas departures, the water supply, the hydrophobicity, and also the porosity of the GDLs and CL. And basically, this is due to the concentrations polarization, because for sometimes, so the water cannot directly transfer to the electrode due to the some issue on the gas bubble management at the anode side. Okay, and this is the polarization curve at different temperature and pressure. And when we see here, when we increase in terms of the temperature, so the performance will be increased. So we can see that the requirement for the energy, so little bit lower compared to the at low temperature. Okay, while when we see in terms of the pressure, it will decrease. It will decrease with the increasing of the pressure. When we see in terms of the energy requirement is increasing with the increasing of the pressure. And this is the summarized in terms of the polarization curve at different electrolyzer technology or electrolyzer types. For example, this is for the alkaline types electrolyzer, which is it has or it requires a little bit higher energy compared to the electrolyzer, and also for the solid oxide electrolyzer. As mentioned before, basically this is basically reflect to the efficiency for these types of the electrolyzer. And we can say that the PEM and SOHC electrolyzers show a greater potential to reduce the capital cost and to increase the efficiency. And so while we know in terms of the fundamentals, so we need to know what is the components of the electrolyzer. Basically, we need to know what is the materials that we use and what is the design that we use to produce the hydrogen, okay, using the electrolyzer. And this is the basic component for the electrolyzer. So basically, we have the fluid plate. For example, this is referring to the bipolar plate. We have the gasket. We have the porous transport layer or gas diffusion layer. Okay, and we have the electrode. Okay, which is we call it the membrane electrode assembly. Okay, which is these components has a symmetry. For example, the anode and cathode are similar components, and the MBA is the heart of the electrolyzer. And so basically, at the anode side, for the PEM types electrolyzer, we use the iridium oxides. Okay, while for the cathode side, so basically we use the platinum carbons, and for the membrane, basically the common materials used is the perfluorosulfuric acid, PFSA polymer membrane. This is the common material for the PEM electrolyzer. Okay, And also, this is in terms of the one of the important component that we need to know is the bipolar plate or the fluid distributor, which is this component is the most important component and give about more than 70% of the total weight. And the functions of this bipolar plate is to distribute the fluid, fluid either gas form, for example, oxygens and hydrogen, and also the water, for example, for the PEM electrolyzer. And then it has a function to spread the cell, to support the electrode, the MEA, and also to facilitating the electrical distributions and the thermal conductivity. And this is the examples of the actual photo for the coated stainless steel and the titanium, which is we are referring to the metallic plate for the electrolyzer. Okay. And this is how we can design the bipolar plate, which is each design has their own advantage and disadvantage. So basically, the design is referring to what kind of the production are you referring to, and what is the how big in terms of the current that are you referring you want to operate for the electrolyzer. Okay, so basically the aim is to have a uniform gas distribution, to have a good in terms of the water transport and good in terms of the mass transfer. This is the goal to design to have this bipolar plate. Okay, and so basically in terms of the electrolyzer, basically we need to apply for the high current. So basically for the high current, the tendency to corrupt is very high. So that's why the bipolar plate, basically we need to coat using a different material. For example, the most common material used for the coating is platinum. And this is the target by DOE, US DOE, for the BOP in terms of the coating properties that we need to have for the electrolyzer. Okay. Yeah, and then after that, we can have, after knowing the components, then we can have, or we can assemble the single cells. Either this is referring to the alkaline electrolyzer, okay, and this is referring to the PEM electrolyzer unit, okay. And after that, we can assemble for the all cells into integrates into complete stacks. We call it stacks for the multiple cells. So basically, for the assembles, the goal is should be no leakage on the on applied currents and fluid. Okay, basically there is no short circuits. Okay, there is no leaking in terms of the fluid, the gas or the water. Okay, and also we need to has the excellent fluid distributor and has a low resistance. Okay, this is just the examples of the photo for the electrolyzer stacks. Okay, and then move to the balance of plant. So basically, this is the system. Okay, this is from the NEL company, one of the hydrogen company. Okay, this is for the electrolyzer system. So basically, for the balance of plant or for the system of the electrolyzer, that basically this is the comparison between the alkalines and the PEM electrolyzer. And basically, we need to have the power conditioning, okay, or the supply unit, okay, the power supply, okay, and then we need to have the reactant, okay, in this case, the DNS water for the PEM electrolyzer and KOH for the alkalines, or even for the anion acid membrane, we have the little bit low concentrations, for example, 1 molar for the AN. Okay, and then we need to have the pressure balancing because we need to have properly managed in terms of the pressure at the anode and cathode side. Okay, because the pressure build up at the cathode side, and then we need to balance the system. And also we need to have the hydrogen cleanup system or subsystem. Okay, for example, this is for the alkaline part. It is alkaline, basically there is some oxygen will penetrate to the porous membrane, and then there is some oxygen at the hydrogen side. Okay, and then before use the dryer. And then while for the pipe electrolyzer, basically we can say that there is no oxygen will be permit or transport from the anode to the cathode. That's why we can have on the hydrogen as a gas and also with the water as a small water, side water. And then of course, the last part is we should have the hydrogen storage. And then basically, when we see the overall system for the balance of plant for the electrolyzer can be operated, basically we need to have the power connection, we need to have the feed water preparations using the pumps and so on. And then we have the pressure balancing system, as I mentioned before. And then we have the hydrogen fill up system to remove the water and to remove the oxygen, for example, at the cathode side. Okay, and also we need to have the hydrogen storage or the buffer tank unit, and also we need to have the thermal management system, because when we operate at very high temperature, and of course there is a requirement to cooling down in terms of the system for the electrolyzers. So that's why we need to have the thermal management system, basically using the chillers or the radiators, and also the last one we need to have the overall control system to properly manage or to link up all the control system for each subunit system. And then, so this is the how importance of the BOP basically, and this is the figures and actual photos for the Cumin products. So previously known as a hydrogenic products. So basically, this is again the comparison for the low temperature electrolyzer, for the alkaline electrolyzer, and also for the PEM electrolyzer. So the important is, so based on the system or based on the BOP, we can manage to have the high purities. For example, using the proper unit of the purification systems, so we can have a very high purity of hydrogen. For example, for this case, the hydrogen can be purified up to 49. Or nearly to 59, 99.998. Okay, this is important of BOP. So if we doesn't proper manage or proper design the system for the purification unit, of course the purity can be affected. And then of course in terms of the operating conditions, so for example, how the system will be operated. So basically we need to manage to have a very proper, for example, farm. So, for example, farm to make sure the operations can operate at, for example, for 30 bar. Okay, for example, this is for the PEM electrolyzer. And also for the alkaline, for example, can we operate at 10 bar. This is basically referring to how you manage or how you configure the system. Okay, and of course, it will affect on the power consumptions. So power consumption, for example, so for the alkaline electrolyzer, so the power consumptions is between 5 to 5.4 kilowatt hour per normal meter cube. Okay, compared to the PEM electrolyzer, which is slightly lower in terms of the energy requirements, about 4.4 to 4.8. So basically, this is due to the because as I mentioned before, for the alkaline electrolyzer, basically they need to have another additional unit to remove the oxygens. So that's why the power consumption for the alkaline electrolyzer system slightly higher compared to the PEM electrolyzer. Okay, and the part is in terms of the sizing, the packaging of the system. So basically, we need to have a proper design, a proper configuration to have a proper compact system. So, for example, for this case, the size of the system is about 40 feet. 40 feet. And of course, this will reflect in terms of the what is the hydrogen flow rate. The hydrogen for the system. So basically, this is basically referring to the efficiency of the system basically we can correlate with the this energy consumption per meter cube. Okay, and then this is another product by the NEL company. Okay, and for this case, these are referring to the alkaline electrolyzer. Okay, when we compare to the previous Cummins products, okay, in terms of the power consumption, we can say for the NEL products is lower compared to the previous one. Okay, this is due to the purity of the hydrogens. So for example, if we target to have a very small or very low purity of the hydrogen, of course, it will reflect in terms of the power consumption. So that's why we need to identify what is the target purity, and then after that we can design in terms of the systems, we can design in terms of the configuration, and then of course it will reflect in terms of the energy density or energy requirement to produce the hydrogen. Yeah, as I mentioned, the purity is smaller than previous one. Okay, and then this is the correlations. Okay, once we have the materials, we have the designs for the stacks, and then we can integrate. And this is the operating conditions, which is it will affect to the performance. For example, the operations, for example, the flow rates, the current supply, the energy supply that you need to provide, the solution concentration, for example, the alkaline solutions. So basically for the alkaline, basically about 30% concentrations, while for the specs of the pump utilizer, basically using the NS water at certain connectivities of the NS water. And of course, in terms of the operating pressure, the operating temperature, and also the energy input for the system. And of course, it will give you indicator in terms of your outputs. For example, the hydrogen flow rates. Okay, what is the hydrogen flow rate per energy input? And of course, the hydrogen purity. As I mentioned before, this depends on the balance of plant, the systems, and of course, the system efficiency. And the most important part is the cost production. This is the most important part, which is currently the R&D is looking for to reduce the cost materials, the cost of the hydrogen. And this is examples of how the electrolyzer operations, and this is for example for the lab scale, and this is what we have in UKM basically. And this is the pump electrolyzer system that we have again in UKM, which is for this system we can produce about 5 kilograms per day. Okay, basically this is include the DNS water system. We treat the water from the tap. Okay, and then we have the pump electrolyzer stacks at 3 kilowatt. Okay. Okay, and this is the system again to purify the hydrogen, to remove the moisture, and at the end we have the 9 figures in terms of the hydrogen purity, and then we store at the hydrogen pressurized tank. Okay, and this is some of the finding that we have. Okay, we study in terms of the effects of the conditions to the performance of the electrolyzers. Okay, and of course what is the energy consumption to produce at per kilo of hydrogen. And this is the again the findings in terms of the input profiles, current and voltage, and this is the output, the operations. This is in terms of the dew point temperature. This is referring to the how purity of your hydrogen. Basically, when we see in terms of the temperature at 59 degrees Celsius, negative 59 degrees Celsius, we can have about the purity of hydrogen can meet about 4 to 5 nines. Okay, and this is in terms of the energy consumption that we can produce per kilogram of hydrogen. And then I will talk about the challenge and considerations. Okay, so the first challenge is basically, yes, this is almost similar to any technology. So the first part basically challenge basically in terms of the fundamental issues. So this is including the electrochemical reactions and also the mass and heat transport. Okay, and also the challenge in terms of the materials, components, developments, including the catalyst, electrode, the membrane, electrolyte membrane, the coating, bipolar plate, and as well as the hydrogen storage. And also the challenge in terms of how you design the electrolyzer and how you design the system. Okay, this include the bipolar plate design, the sealing, the flange, the tie rod, and so on. And of course, at the end, how you design or develop in terms of the system. And of course, this factor will affect directly to the cost. Okay, for example, the material, of course, it will definitely influence in terms of the cost. Okay, including the system stacks and balance of plant, and at the end, it will affects on the efficiency and of course the cost of the hydrogen. Okay, and in terms of the cost, this is the distribution in terms of the stacks and balance of plant. For example, 45% from the cost coming from the stack. Okay, okay, stacks including DCD. Again, for the stacks, we have another distribution. For example, this is for the electrode catalyst coat membrane. And for the balance of plant, this is the category that you need to know in terms of the cost for the BOP, including the power supply, the IS water circulation, the hydrogen processing, and cooling. Okay, and this is how we can consider to reduce the cost. Okay, this is referring to the materials. So for example, at the y-axis is referred to the fractions of the total system cost in percent, while the y-axis, the x-axis is the potential for the cost reductions, which is we can divide into the low, medium, and high. For example, when from the left to the right, so the cost reductions will be increased. So for example, we took the electrode as examples. So basically, electrode, as I mentioned, for example, for the PEM electrolyzer, so they use the platinum and iridium catalyst. Okay, and how they are targeting for the features. For example, they are reduced in terms of the catalyst loading for the PEM electrolyzer, which is at the same time it will increase the performance, and of course it will reduce the cost of the materials. For example, this is the targeting from the current situations, and for the future, for example, the current density at this moment we can achieve about 2, and for the future about 5 ampere per centimeter square, which is very huge performance. And of course, the electrode area, the active area, as I mentioned before, the active area will reflect to the hydrogen polarization for the one cells. And this is the targeting reductions of the materials catalyst. For example, from the 5 milligram per centimeter square, they are targeting to have a 1.2. And the platinum loadings, they are targeting to have from 2 milligram per centimeter square to 0.05 milligram per centimeter square, which is very huge targets in terms of the cost reductions for the catalyst. And then this is the again the cost reductions. The combination of the cost reductions in electricity and electrolyzers combined with the increased efficiency and the operating lifetime, which can deliver up to 80% reductions in terms of the hydrogen costs. Okay, so basically this is the current hydrogen cost. Okay, yeah, this is normal. Okay, so basically even if we consider for the high for the green hydrogen, so basically sometimes the hydrogen cost will be up to 10 USD per kilogram. Okay. Okay, then they are targeting for the future is only 1 point something USD per kilogram. This is they are targeting, the world targeting. Okay, and then this is the cost reductions and the sensitivity analysis in terms of the investment cost. Okay, investment cost to develop the electrolyzer. For example, if the cost reduce, so then you can have the cost of the hydrogen will be low. Okay, and this is another sensitivity analysis in terms of the electricity cost, because the cost basically coming from the energy use, the power consumption to operate the electrolyzer. Then if you have a very low energy price, okay, then of course you can reduce in terms of the cost of the hydrogen per kilogram. Okay, and this is another KPI for electrolyzer technology. Okay, and basically in terms of the pressure, in terms of the efficiency, lifetimes, the capital cost. So, and this is the comparison between different types of the electrolyzer, for example. Okay. Okay, for example, the PEM electrolyzer. Okay. So currently the pressure is we can have about 70 bar or less than 70 bar. And then future we can have more than 70 bar, and it can reduce the cost for the compressor, for example. Okay. And in terms of the efficiency, it will increase from this is the based on the kilowatt hour per kilogram. Okay, it will reduce, and of course if you reduce the energy consumption, of course the efficiency will be increased. Okay, and of course this is another capital cost reductions. Okay, and this is another future KPI for the electrolyzer technology based on the PEM electrolyzer, and this is what the R&D can focus. Okay. So for example, for the current density, so basically we can have we can focus on the designs and on the method or the to develop the material for the membrane, for example. Okay, the catalyst. Okay, and for example, and also this example for the system. So basically, we can focus in terms of the system configurations, for example, the balance of plant, improvement of the balance of plant, and so on. Okay, and this is for the future electrolyzer targeting. Okay, and this is the actual data from 2005 till 2019 for the electrolyzer capacity, the project development, project deployment. Okay. Okay, this is in terms of the cumulative electrolyzer capacity in gigawatt. Okay, and when we see here the projects or the projects or electrolyzer unit will be increased with times. Okay, and this is the estimation projection for the electrolyzer deployment till 2030. And this is estimated necessary electrolyzer manufacturing capacity to meet a different installed capacity target by 2050. So basically, again, the trend is exponentially increase till 2050. Okay, and this is the current project, okay, or future project for the future electrolyzer using the low temperature of the electrolyzer, for example. Okay, for example, the Accelera to power 100 megawatts. Okay, Sembcorp. Okay, this is from Indonesia. They have their own target to produce the green hydrogen by using the electrolyzers. Okay, and also there is several projects. For example, world largest green hydrogen plants construction is 80% completions. This by at the Saudi Arabia nations. and also China also targeting for the green hydrogen, and they have promotes or they develops many projects, especially in Xinjiang at the north of the China, okay, using the solar farm as their energy sources, okay. And this is another news for the future or the current electrolyzer technology to have green hydrogen productions. Okay, and as a conclusion, okay, so water electrolysis as a key technology for the green hydrogen productions. Okay, and basically we need to have the policy roadmap and strategies are required for the technology deployment, and of course we need to have the comprehensive ongoing R&D, which is to cut the cost as mentioned before, to reduce the cost and to boost the durability and also the efficiency, and of course the target is of course in global large scale projects, which is can be driving the progress toward the net zero emission by 2050 and fostering economic growth. Okay, I think without that, I think that's all from my presentation. Thank you, and maybe I pass back to Dr. Ryan. Thank you.
Thank you very much for Dr. Syafruddin for the interesting talk in the hydrogen, and also there's many broad range of the talk. Start from the division of the hydrogen, the conversion device for the hydrogen, support the operation of the PEMFC, as well as the future and what we can do in the future for reducing the cost of the hydrogen production. There's a lot of question in the chat box, and probably you want to also ask directly to Dr. Syafruddin. But before you can Dr. Syafruddin ask the question, so we would like to move into second presenter. Is that okay? Thank you very much for Dr. Syafruddin. I will see you again during the discussion. So we have Dr. Aziana. So I will read her biography, short biography for Dr. Aziana. Dr. Aziana is a key member of the Hydrogen Energy Solution section within the Metrology Laboratory of HYOKI Corporation. She is directly involved in advancing the company innovative work for the measurement in the hydrogen energy field. And Dr. Aziana earned her Doctor of Engineering in Electrical and Electronic Engineering from Hsinchu University as a recipient of the prestigious MEC scholarships. Her doctoral research, which focused on sensor technology and its application of impedance measurement, is now instrumental to her work in inspiring solutions for the energy challenge of tomorrow. So I would like to thank for Dr. Aziana who can present today. So Dr. Aziana, anytime you're ready, so please start your presentation. I cannot hear you.
Thank you very much. Sorry, the microphone.
Okay,
Thank you very much,
please start.
Mr. Chairperson. Let me share the slide first. So a very good morning and Assalamualaikum warahmatullahi wabarakatuh to everyone. Before I begin, let me just briefly introduce myself. My name is Aziana. I am working in Hydrogen Energy Solutions section in HYOKI EE Corporation, Japan. I'm from Malaysia, and I actually graduated my master and bachelor from University Putra Malaysia, which is just beside UKM, very close. So I joined this company after I graduated from Hsinchu University. My major is basically on electrical and electronic engineering on sensor technology. So basically that's how I also interested in this company, and I joined this company. And I guess that's all for my introduction. So let's us begin with the presentation today. So my title of my presentation today is Hydrogen Harmony with ALDAS, Pairing Impedance Measurement with Evolution of Electrolyzers and Fuel Cell. So HYOKI was established in 1935, and we are proud to celebrate our 90th anniversary of excellence in measurement. And this is the company. It's surrounded by mountains in the middle of, it's very nice and in nature, surrounded by nature. So this is where we do our manufacturing as well as the development, product development as well. HYOKI EE Corporation is an electrical measuring instrument manufacturer. Our business also comprises of various category. We go from small type handheld or field measuring instrument to electronic measuring instrument and data recording equipment and automatic test equipment, the largest in our company. So we are basically focusing on electrical part of the measurement. And our business domain is to solve social issues through electrical measurement. By visualizing the conversion of efficiency from electrical energy to various forms of energy. So I choose, there's four type of energy, for instance, from electrical energy to various form of energy, from various energy to electrical energy. HYOKI provides service and product to accommodate this technology. So we can visualize them. So the HYOKI core technology is based on several parts. One is the power impedance and measurement. We also have high accuracy wideband software, as well as high accuracy, high precision wideband, high current sensor. So with these core technology that we have in HYOKI, we create a system called ALDAS, specifically for impedance measurement system for electrolysis cell and fuel cell. So what is ALDAS? ALDAS is short form for Active Line Device Analysis System. An ALDAS system consists of 3 modules: source module, sense module, and control module. Let's take a water electrolysis cell as an example. Okay, when we operate the water electrolysis cell, we will have a DC power supply, and we will have electrolysis cell that is producing hydrogen. And the line we call active line is the line where the electricity flow. So what does ALDAS do? First, we will apply the alternating current to the active line from the source module. And then we measure the current and the voltage from our current sensor and voltage sensor. And then from our control module, we use our integrated analysis software to plot an impedance graph. This is the example of the graph that you can get from our software. It consists of IV plot and Nyquist plot. The IV plot is, as previous presenter has presented, is also called polarization curve. And in addition, ALDAS can also plot the Nyquist plot together with the IV plot and its COCO plot. And this 2 graph is very important, which what I will cover on today. So this is the flow of my presentation today. As for introduction, I think this introduction is also been covered by the Prof. Shahbuddin previously. Hydrogen is a versatile energy carrier. It has high energy density, and it's also abundant. It's available in various forms as not just water, but also in hydrocarbon. It's also versatile. It's not just can be used as a fuel, but also as a feedstock, produce ammonia and methanol, so forth. And what is special about hydrogen is it is clean at point of use, where there is no greenhouse gas emission at the point of use, and the byproduct is just water. For the sustainable pathway, first we start with water electrolysis cell, which requires water and also electricity source. If it's from renewable energy, it is called green. If it's from other sources, we have different color for them. Now, from water electrolysis cell, we produce hydrogen. And then this hydrogen, what are we going to do with this hydrogen? We can also use this hydrogen for electrolytic synthesis to provide with toluene, with carbon dioxide, with nitrogen to produce various, like MCH is a carrier, like e-methane is a synthetic fuel, and ammonia that can be used in various part of system. And this is called the power to X concept, where the electricity conversion, energy storage, and conversion pathway is used from the surplus of renewable energy. And this technology also allow decoupling of the power from the electricity sector and be independent on its own. So it can be done in very secluded area if you can produce this on the spot. Previous Prof. Shabuddin also did mention about the color of hydrogen. So I actually summarized this color of hydrogen into several this graphic. We have renewable energy, green energy, green hydrogen, and also we have like pink and purple for nuclear, and also black, brown, gray for fossil fuel, non-renewable resources, and they categorize as dirty color. And also clean renewable energy and clean green energy. Green hydrogen is basically what is our target. So the emphasis of the whole hydrogen is to be produced in green as from renewable energy. So these are just some of the processes that make them different color, but I think this is just additional information. Next, we are going to the FC and EC. So we have the hydrogen molecule as from the introduction. Now is the equipment that uses this hydrogen. So fuel cell and electrolysis cell are both used in hydrogen process. Fuel cell uses hydrogen as for combustion by some spontaneous reaction that produces electricity, with byproduct is water. And electrolysis cell uses the electricity to produce hydrogen, and byproduct is oxygen. And as I've written here, there's a spontaneous reaction and non-spontaneous reaction. Electrolysis cell requires energy, which is the electricity to drive and break the bond of the water molecules into hydrogen and oxygen. So we can say that this processes is like two sides of the same coin. It's interchangeable, and it's very important in terms of hydrogen technology. So these are the overview of the processes inside fuel cell and electrolysis cell. Both are redox reaction. I normally say one is oxidation or one is reduction. Oxidation is when you lose electron, reduction when you gain electron. So both processes exist in both fuel cells and electrolysis cell. So this has already been covered by previous presenter. I will not cover this part, but I would like to just briefly introduce this type of fuel cells and electrolysis cell. The fuel cell and electrolysis cell do have something in common in terms of what types, like for example, proton exchange membrane, which is the H+ is proton. So they use this technology also for fuel cell, not just electrolysis, and also for solid oxide. Solid oxide is quite special. It is reversible. You can use it as a fuel cell. You can use it as an electrolysis cell. It's just the operating temperature is very high. The water is in the form of steam, and like in PEM type, they will use catalysts to assist on breaking the bond, of course, with electricity. But in solid oxide, you just use ceramic, and the kinetic energy from the temperature of the steam will break this very strong hydrogen-oxygen bond of water. So I think more of the details was being covered previously. I will not talk detail, but this is the one that is very interesting because our measurement technology also do cover almost all of these cells. Now, let's go to the measurement technology. Hyoki is a electrical measuring instrument company, so let's learn about measurement technology. In this part, I separated into 4. First is the IV graph, impedance, electrical circuit element, and the 4th is overcoming the limitation of IV graph. I'm sorry, can the speaker mute?
So for the audience, could you please turn off your speaker?
Okay. Okay, thank you. So first I will cover on the IV graph. So from previous presenter, Prof. Shahbuddin also mentioned about IV graph. And it is also known as performance curve or polarization curve. This IV graph helps to understand the operating efficiency of the entire system. And that's why from previous presenters will cover a lot about the IV graph data that compare with various different kind of situation, operation condition. So it is very, very common to use IV graph for fuel cell and electrolysis cell. The fuel cell that generates electricity, the IV graph plots the output voltage against the current density being drawn, and the electrolysis cell, on the other hand, consume electricity, split the water molecule, and the IV graph plots the voltage against the applied current density. So these are the graph for fuel cell and electrolysis cell. They are the opposite of each other. It's a mirror of each other. For fuel cell, in the beginning from OCV, you will see the voltage decreases. OCV is the maximum for the fuel cell, and it's a minimum for electrolysis cell, the opposite. So at the first part, the voltage, high voltage indicates a better performance. As the current density increases, the voltage will be reduced as more current is being drawn. On the other hand, for electrolysis cell, as the current density increases, the voltage increases because there is a lot of variety of losses that occur in the cell that require the voltage to overcome this resistance and produces more current. Okay, let's take this fuel cell and electrolysis cell. Generally, this true IV graph is separated into 3 area. First is the first part, the activation loss in fuel cell or activation over potential. The terms used in electrolysis cell is over potential. The terms used in fuel cell is loss. So the same activation, ohmic, and concentration loss, and these 3 different parts. First, let's look at the lowest current density, which is activation loss. This activation loss is the energy required to overcome the initial barrier and to start the electrochemical reaction of catalyst on the fuel cell, and activation over potential is the energy needed to overcome so that you can do the water splitting on the electrode surface. From the graph, you can see that there's initial drop, and for electrolysis cell, initial increase. And the next part will be the ohmic loss or ohmic overpotential. Why it is called ohmic? Because it shows similar behavior as the Ohm's law, the linear, almost linear in voltage in both sides. And then the last is the concentration loss. Concentration loss occurs in the high current density area where the system for fuel cell that the system cannot supply the fuel cell like the hydrogen and oxygen fast enough to meet the demand for the high current. And for the electrolysis cell, there is a build up gases from this splitting reaction on the electrode surface that block the active site to make it harder for the reaction to process, hence increase in resistance as well. So there are few limitations from the IV graph that we cannot identify. First, we cannot separate the different voltage losses that occurred in the cell because it shows the combination of losses of all voltage, and it cannot quantify what voltage, how much loss and what process on a specific losses is. And from this graph as well, we cannot learn about the degradation performance because as the cell ages, the IV graph will look worse, but then it does not show what is the part in the cell that is degrading. The next one will be the specific component resistance. Like the linear ohmic region gives the total area specific resistance. It does not really break down to individual resistance of the component that is required to identify the problem. And also, IV graph in a steady state, it does not provide information about how the cell responds to rapid changes or about its internal capacitive properties. The dynamic response of the internal state is not visible. You can't identify from this graph. Now, before I go for the more on the impedance measurement, let's learn a little bit basic about impedance. So let us have a system. This system consists of input and output. You input the DC current and you will get output as voltage, constant voltage. And with Ohm's law, it is a linear system. Yeah, we can identify, oh, this is a resistor. Now we have another system. We input the same DC current and we have this result. It is a nonlinear system. How can we identify this particular black box? We use the AC current, and then we get the information output in terms of the sine wave. And this is what we call as impedance, where it is a quantitative measure of a circuit's overall capacity, not just for resistive, but also inductive and capacitive component. And we can also make in accordance with the Ohm's law. So let's take this time domain measurement, where we measure the current and voltage. Next, we transform it into complex domain. And this are the vector representation of the impedance as a complex number. And from this complex form, from each measurement, each frequency, then we can plot. This is called a Nyquist plot or COCO plot. It is an impedance spectrum where it sweeps normally from high frequency to low frequency in the complex impedance plane. And it is constructed point by point from a series of single frequency measurement that transform from time domain into the complex domain. Now, the impedance, generally, we have this time domain that looks like Ohm's law, and then we transform to the complex domain, and where we have real parts and imaginary parts. In chemistry, probably they will use Z prime and Z prime prime, but in electrical, from background, we like to use the R and X. X is the imaginary part. and it's basically referred to the same thing. Okay, so on the right side, you can see this imaginary axis and real axis. We have a point, and the magnitude of the impedance is, and also we can get from phase from this information as well. Now let's go to electrical circuit element. Let's go back to basic. First, resistor element. The same complex plane. We can plot the resistor. So the resistor will be at this point where on the real axis, it's a real value, and there's no imaginary axis, it's 0. So we know that R is at this location at that coordinate. How about capacitor? Capacitor, as you can see, it is not linear, but it does respond to various frequency. From low frequency to high frequency, there's a pattern. From low frequency, as the frequency gets higher, it becomes short circuit. Low frequency, it's like open circuit. Conversely, for inductor, at low frequency, it acts like a short circuit, like short wire. That's why the impedance is close to 0. But at high frequency, it stores energy and it becomes, the impedance gets higher, and that's where the resistance gets higher as well. Now we combine the R and C in series. We can see that we just shift the the capacitor from low frequency to high frequency point, just shift it to the right with the value R. How about R and C in parallel? Because the R and C in parallel, it will look like this, like a semicircle. Let's just learn about this semicircle. First, we will have a high frequency. At high frequency, the capacitance value will be short circuit. This means that so we have the value of R, and then in the middle, so it will combination of the R and C, and then at the low frequency, the current, the capacitance will be having higher impedance at low frequency, and so the pathway of current will be through the resistor. This I take an example for a PEM type of EC system where we have the R charge transfer and resistance for mass transfer. And with this representation, I will explain about how the graph and this value relate. So the first is the ohmic resistance. Ohmic resistance is the resistance of the membrane due to the proton conductivity of the membrane. And then we have charge transfer resistance of the catalyst layer. We have double layer capacitance. We have resistance due to the mass transfer, and also the mass transfer capacitance value, which can be identified from the plot that we see just now. So we have another terms. It is called electrochemical impedance spectroscopy. So why it is called electrochemical impedance spectroscopy? Impedance is a very general term. It exists in a lot of systems. So EIS, electrochemical impedance spectroscopy, related to chemistry. So it is electrical properties of a chemical system with the impedance. Spectroscopy is because it's like sweep on a range of frequency. It is an analytic technique where we can use to study this system, and it involved by applying small AC voltage or current. For other system, we use AC current to the system, and we measure the results in voltage or current response. So by analyzing how this impedance varies with frequency, the EIS can provide very valuable information about different processes that occur within the cell. For instance, the fast processes are captured at high frequency, like the ion flow-through membrane, and the slow processes are captured at a medium frequency, like electrochemical reaction at the catalyst, and very slow processes are captured at low frequency, like a gas diffusion, the molecules. Previously, I mentioned about the limitation of the IV graph, that first, we cannot separate different voltage losses. As you see before, there's a EIS can provide the separation of a total resistance into a distinct component like ohmic resistance, charge transfer resistance, as well as the mass transport resistance. Second, the root cause of performance degradation. The curve does not tell what degrade. By using this EIS impedance graph, we can do diagnostic by tracking how the impedance, the EIS spectrum changes. An increase in charge transfer resistance will point to catalyst degradation, while increase in ohmic resistance probably suggests membrane issue. Third is the specific component resistance, where we can't identify. So, for example, EIS at high frequency, where the intercepts 0, plot give a precise measurement that point is purely ohmic resistance and isolated the value from the other process. The last one is the dynamic response. Since the EIS is normally measured in active state, so we cannot just know the dynamic response with IV graph. But with EIS, the shape and the size of the arc of the EIS plot can be used to diagnose the internal state, or such as membrane hydration or electrode flooding. So we can get more information with the impedance spectroscopy graph. Let's look at the example of case study. There are two types of a case study that I'm going to present today. Both are related to PEM type electrolysis cell. First is operation at different current density, and the second one is comparison with different catalyst load. The first one is the operation at different current density. First, we get the IV plot. This is a normal plot that we can get. And then there's the EIS graph. As the current increases, what we can observe is that the charge transfer resistance decreases. We can see from the size of the semicircle decreases from the 1 ampere is the blue one, and then 20 ampere is the red one. So it gets smaller as the operating current increases. So this is the same together with the EIS graph and IV graph at low current density, represented by these 3 points. We can see that this is the graph, and then when we increase the current density and also at the higher current density, which also, as I mentioned, it corresponds to different parts of the electrochemical reaction occurs within the cell that we can identify by having this impedance graph. Next is the comparison with the different catalyst load. So how we actually compare this is by using different value of the catalyst. For new, we represent it with the iridium 2 milligram per centimeter square as a high catalyst load, means new. Use is with 1 milligram per centimeter square, means that as this system in use, the electrolyzer operating for many hours, and the catalyst load decreases over time. So we represent the low catalyst load as the use. So the orange and the blue line, we can see some observation. The first observation is how it is shifted up. The voltage increase So means the voltage for the use electrolyzer is more. The voltage is more. Means something happened. There's a resistance happening. Something happened in the system. The next observation is the gradient of this graph. At the higher current density, the gradient increases and the use seems to increase steeply instead of gradually. So something also happened at the higher current density, but we don't really particularly know why. So that is why we're going to answer it by looking at the EIS graph. So I'm going to take 3 points at 10, 25, and 40 ampere. So these are the PEM type electrolytic cell system equivalent circuit. First, we will look at for this one is our solution, which is the ohmic resistance. At high measurement, the frequency of the imagined part can consider as 0. So we can look at the difference between the used and new. And as you can see from this graph, it is obvious that there is shift. The graph shifted to the right. It increased in its resistance. So we can get the differences of this ohmic resistance and the degradation that happened. That is only the ohmic part. The next part is the two parallel this RC circuit in series. The first part is the width of the first semicircle, and the second part represents the width of the second semicircle. And this is the IV graph that from the beginning. When we look at the 40 ampere, it seems like the mass transfer diffusion is dominant on the second, the higher current density, the mass transfer resistance is dominant. You can observe from the EIS graph. So that will be the case study. And next, I will talk about from data to decision. As a summary, what can we get from the impedance data? First, we can evaluate its performance because we know about the resistance, the charge transfer, mass transfer limitation, and then also we can diagnose and troubleshoot the system. We can identify and detect what degradation happened before it actually melt down or some accident happened. We can diagnose it beforehand. Third, on the research part, we can do optimization and design improvement. With this evaluation test, we can do better material selection and design the better cell architecture. From EIS, also, we can understand the fundamental processes happening, what occur in the cell, such as electrokinetics and interfacial phenomenon. For manufacturing side, this information is valuable to ensure the manufacturing consistency and also benchmarking and comparison, as well as producing some sort of protocol and standardization. 6 is the durability lifetime assessment, which is commonly being done, such as aging studies and stress tests. After you design this membrane, you need to optimize it. And also for lifetime assessment, we use the same EIS data to compare each part of the flow when for both electrolyzer and also fuel cell. So what are possible risks without the impedance measurement? There is a decrease in the performance of the fuel cell or electrolysis cell and reduce its efficiency and lifespan without we know about it. And it is because it is undetected degradation. And there's also possibility of failure due to the misdiagnostic diagnostic opportunity. Of course, there's also limited information you can get from the system. There's also limited R&D exploration because exploration of an R&D highly depending on how much data and what we can get from the system. High operational cost, as it's degrading, the resistance build up, the voltage increases. Hence, you require more electricity, more power to be supplied to the system in order to get the same outcome. For example, like the volume of the hydrogen that is required will require more electricity. So hence, it is high in operation cost. Now, how EIS can accelerate innovation? It can be used together as the predictive maintenance and to monitor the system to prevent failure, and also can be used to improve for durability tests and used as a diagnostic mechanism. With EIS, as I mentioned before, you will get more information about the system. Hence, you can ramp up the R&D exploration for the targeted material development and new catalysts for the electrolyzer or fuel cell. By understanding the degradation mechanism, the researcher can design to build a long-lasting cell and make it durable when we understand more about this material with the EIS data. Now I'm going to talk about the active line measurement technology that we are using in our product. So what is active line measurement technology? It's basically the measurement technology that visualize the characteristic that only visible during operation, not just as in static, but also in a dynamic condition, but actually basically mostly on the dynamic condition, where we get to measure the characteristic of the specific target, which from the closed circuit that is made up of other parts and devices, because electrolysis cell does not it is not on its own. It is connected to different, obviously, forms of DC power supply and so forth. So this kind of not to say intervention, but this kind of the outside that might interfere with the measurement. So this is how we connect our ALDAS measurement system. It is not together with the system of the electrolysis cell. Electrolysis cell can operate on its own. Our system just attach our clamp sensor to the wire of the active line that connects the DC power supply to the water electrolysis cell, and we measure the voltage. And also, we also need another cable for the source module, which is to input the AC current for the measurement. From our system, we can have the Nyquist plot or COCO plot, the impedance graph. Together with the IV plot, it is measured, it is plot simultaneously. And also we can do the impedance logging at a specific frequency with our measurement system. So why do we need active line measurement? Like I mentioned before, the water electrolysis cell is not on its own. It is connected to the DC power supply, external DC power supply. And this composite of this arrangement is not the characteristic of the cell itself. It's so user can't tell the difference. So they just measure, but then we actually measure the cell or we measure the whole system. So that is where we go to the next part about current divider effect of AC measurement current, because EIS is closely related to applying the AC current to the system. So this effect might also affect the measurement. The effect of this current divider occurs when the DUT is operated by an external DC power supply, where the AC measurement signal injection point is attached in parallel to the active line of the DUT, and is based on the Kirchhoff law. So you see, the source cable will inject the measurement. We call it measurement signal in terms of the current signal. So this measurement signal will split at this point before the DUT into this two component, one to the power supply, another one is to the DUT. And then these are also combined again at this point. So the AC measurement signal is actually, they have on the DUT side, and also is a summation of the DUT side as well as the DC power supply side. So normal conventional EIS device measure both of this. And for ALDAS, we only independently only on this DUT side. Let's look at this comparison. Why it is why we measured the true, because we measured the current that passed through the part where it really passed through the DUT. But for the conventional EIS device, when you have the DC power supply externally applied, they will have they don't have the current sensor that actually connected to this, because you can't modify the system that's already there. So what they do, they have internal measurement which measure the current signal. So basically they measure the whole thing. Hence why we will get this small circle at high frequency side, because the parallel connection between the EIS and DUT leads to an overestimation of the DUT impedance, where the EIS device measured the combination of the impedance of DUT and power supply, not the DUT itself. We don't want the whole thing. We just want the DUT what I call EIS measurement. So this is how the measurement technology that we've established in our company, that we would like to emphasize, that we measured the current that flow through directly to the DUT and not the whole system. Now I'm going to just briefly introduce about our product. So why measure impedance with ALDAS? ALDAS, we are able to measure with high current or high for EC, both EC and FC, because it is designed for industrial size electrolysis and fuel cell, because of our current sensor technology that can measure really high current up to thousands of ampere. With the available range of other EIS measurement instrument, probably around this range, and with ALDAS, we can measure higher current, not just 2000 ampere. We can have them in connection, and we can have multiple. So we can have up to 8000 ampere if required, if the customer system is beyond that range. And no modification is needed, because as we have our clamp sensor, you just clamp the current sensor at the wire, and you don't need to actually modify the whole electrolysis system just to fit in the EIS measurement system. And conventional method, since they cannot accommodate high current, and they need to make a very small scale, like 1 by 1 centimeter square. But with ALDAS, we can measure high current. Hence, we can just measure it, the size. We don't need small scale tests. We can test how big, depending, of course, how big your MEA is. But we do have this technology to measure very high current and very big scale of from the 1 by 1 centimeter square. And ALDAS also, we have a multi-channel measurement, and it is a simultaneous measurement. It is not like delay. There's no delay. It is a true simultaneous measurement, multiple stack. For instance, in multiple cells in a stack, like for instance, it's the same stack, multiple cells, we can measure it directly up to 24 channel. So for who do we provide solution? So our target is a researcher, obviously, to implement the first step towards the social implementation. So this is the line: research, development, commercialization, and industrialization. This is the pattern that we want to realize this hydrogen society. So it starts from research, and now we're at the development. And each section, research to development to commercialization, there is a hurdle that you have to overcome. And at this point, from development, you already develop a very good cell. But then when you want to commercialize it, you need to go bigger scale. But you can't go to bigger scale because there's no such evaluation system that can measure it. So we want to provide value solution that match with the practical environment and to promote the social implementation of the hydrogen technology up to industrialization. So these are the two of our customer from Advanced Institute of Science and Technology, Japan, which both for PEM type electrolysis cells and solid oxide, and they use it to evaluate the aging tests in industrial scale. And JAXA also use ALDA's product for the Sabatier reactor, basically for the carbon dioxide. Now, last but not least, this is our product lineup that we have so far. We launched ALDAS Mini this year, which is a smaller type of ALDAS E. ALDAS E currently is only custom made, and ALDAS Mini is commercially available as a standard product in Hyoki. Depending on your requirement, please contact maybe Hyoki representative for more information on this ALDAS product. Thank you very much for listening to my presentation today. That's all from me.
Thank you very much for Dr. Raziana. It's very interesting talk in the measurement technique, not only the hydrogen, but also in the measurement technique, especially the impedance. And you explained a lot how we can analyze the impedance and also IV curve. So now we are moving to the discussion session. Is that okay? So Dr. Syahbudin is with us. Okay, thank you. So we have two audience that want to ask directly to you. So I will present Tridila Usma from University. So please ask your question.
Baik, terima kasih atas kesempatannya. Sebelumnya, apakah suara saya sudah jelas terdengar?
Iya, silakan.
Baik, sebelumnya saya izin menggunakan bahasa Indonesia agar lebih mudah dalam proses tanya jawab. Perkenalkan, nama saya Tridila Usma, asal saya dari Universitas Syah Kuala di Aceh. Terima kasih saya ucapkan kepada dua narasumber yang hebat dan luar biasa, yaitu Prof. Syahbudin dan juga Dr. Aziana atas penyampaian materinya yang sungguh insightful, sangat menginspirasi dan bermanfaat untuk kami semua. Di sini saya izin bertanya dulu Pak Prof. Syahbudin. Yang pertama, bagaimanakah strategi efektif dapat meningkatkan terjaganya penguatan yang lebih kokoh lagi dalam meningkatkan potensi elektroliser suhu rendah untuk produksi hidrogen hijau dalam emisi untuk mencegah emisi karbon lebih berbahaya lagi gitu ya, agar semakin terjaga sustainability atau pengembangan terjaga lebih efektif lagi. Kemudian yang kedua, menurut Prof. Syahbudin, bagaimanakah kolaborasi efektif yang diharapkan dan ditingkatkan lebih mendalam lagi, baik dari segi pemerintah, sektor LSM, masyarakat, untuk saling berkontribusi dan berpartisipasi dalam meningkatkan penguatan dari elektroliser suhu rendah untuk produksi hidrogen hijau untuk peningkatan teknologi semakin maju. Kemudian untuk Dr. Aziana, izin bertanya. Pertanyaannya adalah yang pertama, bagaimanakah cara mengukur sejauh manakah dan seberapakah potensi keberhasilan dalam memasangkan pengukuran impedansi dengan evolusi elektrolizer ini untuk dapat kita jadikan suatu evaluasi ke depan terhadap hal-hal yang perlu lebih diperhatikan dan dikembangkan. Serta yang kedua, menurut Dr. Aziana, bagaimanakah kita ini dapat meningkatkan soft skill dan juga hard skill ke depan untuk terus menyukseskan dan mengembangkan dari potensi pengembangan dari evolusi elektrolizer dan sel bahan bakar. Sekian pertanyaan dari saya ucapkan terima kasih.
Thank you for Tridila Usma. Terima kasih untuk Tridila Usma. Dr. Syahbudin, please, you can answer for the question first.
Okay, terima kasih Ibu Tridila. Boleh dengar? Alright. So first questions is on the strategy kan, strategi electrolyzer. Bagaimana untuk perkembangan. So basically strategy. So the strategy basically, as I mentioned before. So basically,
beli makan.
basically that one depends on first, of course, depends on the policy makers lah, policy government directions. So from that directions, then they come out the policy, the standards, and bila ada that kind of the movement, so the industry, the academics, the communities, then know about the technology, about the aims of the national agendas, and then from that part, so of course when we develop the policy, when the government develop the policy, and of course they will give some fundings. So funding. So bila dapat funding itu, then the researchers can come out the R&Ds. So this is the first strategy, basically, the R&D. So once you have the R&D, then you can improve all the parts, all the components, all the materials, all the designs to make the electrolyzer, especially for the low temperature electrolyzer, can be used in terms of, I mean, the cost will be reduced. The cost, once you have the cost reductions, then you can deploy easily the hydrogen production by using the electrolyzer. Okay, so maknanya, so first on the policy maker, the government's rules, and then of course the academics in terms of the R&D, and then further on the industry. So on industry tu means they kena deploy everything lah. So they need the perlukan manufacturing everything. And then at the end, lastly, of course, the community levels lah. The community levels basically, so of course, the citizen lah will get the facilities kan, based on the hydrogen production. So ni termasuk application for the hydrogen lah. Contohnya fuel cell everything lah. Okay, that is my first answer for the first questions. And the second one in terms of the kolaborasi. Kolaborasi tu basically in terms of, so basically bila kita buat certain technology, so we need to take care for the four part, for item lah. For item basically first, of course, community lah, rakyat, citizens. Then industry. Back to the first soalan tadi lah, industry. Then of course the governments lah. So maknanya these four parties need to have a very good connections. Good connections. For example, of course, academic then. Academic basically they can take a role for the awareness. Dia similar lah, academics and the governments kan. Since as I mentioned tadi, kita dah buat certain policy kan, ataupun certain standard, then we need to deploy. Bila deploy itu maknanya every citizens must know lah what is the goals of the government. So termasuk awareness lah. Awareness means that we need to go to schools, then brief them in terms of the what is the new technology to sustain the environment. The environmental friendly. So one of them is hydrogen technology lah. Yeah, of course, educations from the primary schools, the secondary schools, and also the university levels lah. So everything we need to cover in terms of the awareness, and also the community lah. Community basically we need to go to a certain community to, for example, we need to deploy certain technology. For example, in our case, basically we try to install or deploy electrolyzer technology and fuel cell into the origin kampung. Kampung orang asli lah, basically. We try to deploy that one. That one basically from the funded by the our ministry lah. So basically that kind of the awareness or information that we can distribute to the communities. Then again, the government tadi policy everything tadi industry of course that they will fast in terms of the deployment of the manufacturing. So they need to have a very proper technology, for example, to fabricate, to get a very good precision and also the performance everything. So this is how we connect to make this technology happens in our nation basically. So that's from me lah.
Okay, so I continue sambung. There's two questions for me, which is ukur impedance, basically like evaluation. What does it like? What does it do? Basically, measurement is like a type of like learning to understand another language, like a language of your impedance cell or like the electrolysis cell. You want to know whether it is healthy or not healthy. You will know the efficiency. So from this measuring instrument, you know your electrolyzer or fuel cell is probably not healthy, and hence it requires more energy. So means like you cannot save electricity. You keep on using a lot of energy to produce the same amount or even less. So I think it will be beneficial for us to be save energy in terms of electricity that we generated that obviously is in high demand. So we try to use as much as possible by increasing the efficiency of the system. And the second one is soft skill and hard skill. I actually don't really get the soft skill, hard skill. Is it on the human side or the instrument side? But in human side, of course, you required like hard skill expertise on the technical part. Background in various field is possible. And then soft skill, of course, you need to learn, keep up to date with the system, and then try to be open-minded and helpful, learning, communicate with people, and yes, and adapt. I guess that will be my answer. Is it okay?
Baik,
Okay,
terima
for
kasih
you,
banyak kepada Prof. Syahbudin dan juga Dr. Aziana atas semua penjelasan dan juga jawabannya sangatlah jelas, sangat menginspirasi dan bermanfaat untuk saya ke depan. Terima kasih banyak atas jawabannya.
okay, thank you for Dr. Aziana and Dr. Syahbudin. And I would like to move to second one. So, Tenek Ringgubaya, you have question, so you raise your hand.
Thank you.
So please.
Yes, thank you. Yes, thank you. All right. Good morning, everyone, and thank you for the chance. Is my voice come to you? Is okay? Yeah. All right. Thank you. Thank you also for to Ifhe and Brin to accommodate this discussion for all of us. And maybe the first question could be going to Mr. Syahbudin and Mbak Aziana, maybe Kakak Aziana. First question is about talking about feeding water for electrolyzer. Is some people or some researchers said that electrolyzer is supposed to feed it with a demineral water. What do you think if the electrolyzer is not coming from the demineral water, but like river water in the forest? So it's really really natural. So what is the problem if we use tap water to the electrolyzer? Actually is a probably problem is corrosive or something else. If the sedimentation clear enough to can be solved. I mean if the sedimentation problem can be solved in our power plant, can we use directly the river water to the electrolyzer for the water feeding? But that was the first question, and the second one, how many questions I have a chance to ask? Sorry.
So you have one more question, if possible.
All right, thank you. Maybe it could be like kind of
So, what's it? This answer. So, maybe she will come back. So, would you mind to? We have a lot of questions in the chat box, so I will move into chat box question first. Is that okay?
So I will answer from that question.
Okay, sure.
Okay.
Yeah. Yes.
So, okay. So, so she asked about the using directly river water, right? So okay, basically yes, yes you can, but in terms of durabilities, so what might be happen? So long lasting in terms of the electrolyzer operations. Yes, you can, as I mentioned, because in river water you have a lot of minerals, right? Minerals. So basically, for example, for the PEM electrolyzer, basically we need to have there's a certain specifications to have water as raw materials or reactant for the electrolyzers. So once you have a certain minerals, so probably it will affect on the reactions, related reactions, and also of course durabilities and so on. So of course, but in current technology, basically there is technology we can use directly that kind of the water. For example, in current technology, they use directly seawater. So seawater, they just pump into the electrolyzer system, and then they can produce the hydrogen. So basically, that kind of the technology basically referring to the what kind of the material that you use. Of course, you need to develop a proper membrane, electrolyte membrane, and also of course the proper catalyst as a materials. So I think that my answer. Yeah.
Thank you for the answer. So, probably, so it's okay. I know I'm moving to question in the chat box. So there's a lot of question in the chat box. So,
all right.
I will start from Reza Hashim Zakarian Shah. So the question to Dr. Shahbundi. Is that okay? So given the mounting pressure to decarbonize within the tight timeline of the Paris Agreement, do you think the global community risks overemphasizing the role of low temperature electrolyzer as a near-term solution, while underestimating the structural bottlenecks such as water scarcity, renewable energy intermittency, and cross-border infrastructure for hydrogen distribution? And how should this paradox be addressed strategically? That's the question. So quite long question.
So I'm catching the challenge, global challenge. Is that the question?
So his question is because, sorry,
the role
I
of
will read it. So the question is, there's a paradox because if we use, is it possible to use low temperature electrolyzer as near-term solution? However, we also have some problem with the structure bottlenecks such as water scarcity, renewable intermittency, and cross-border infrastructure for hydrogen distribution. So even we use this low temperature electrolyzer as near-term solution, but actually we have another problem about the water scarcity and anything else. So that's the question, I think. So
basically, yes, there's a challenge. As I mentioned, there's a lot of challenge currently. So including basically the cost. As I mentioned previously, the main thing is the cost. So basically the cost will be related to the materials and how you operate, how the system develops. And because the cost is very related to the how the energy that you get, how the price that energy that you get. Okay, this is related to the cost. So basically and currently, so the electrolyzer use the grid electricity. So you can say still in yellow color form. If you use the grid, of course the yellow color form compared to you use the solar or wind. So we can say that it's in green. So of course, the limitations for this electrolyzer, of course, as I mentioned, the price, the cost. So if you get the cost very low, because the most OPEX contribute to the cost is electricity. So once you get the low cost, so then you can get the very low cost of the hydrogen. So this will be effects on the global challenge lah, the global community. So basically in terms of the cost, and of course in terms of the they mentioned about the water scarcity. So as I mentioned before, yes, you have the challenge for to get the water because there's a demand for human as well. So as asked by the previous participants about we can use the river waters, or as I mentioned before, also in terms of you can use as well the direct seawater. So, but the thing is, you need to develop some things. You need to develop suitable materials to get the proper durables, high efficiency of the hydrogen production, and at the end you can get a very low cost of the hydrogen. That's the point and the main thing that we need to handle because there's a lot of cost reduction that we can make it. Okay, is that?
Thank you.
Okay.
So the keyword here is that if we can make a low cost of the material, and also we can make a low cost material cell. I mean that we can also reduce the amount of the price of the cell. So it will also greatly affect for the commercialization.
The first thing is CapEx coming from the materials, right? So the second thing is on OPEX. OPEX, the energy requirement, the energy price to use to break the water for the hydrogen production. So two main things CapEx basically for the materials or design everything, and secondly on the OPEX wise, which is basically on the energy that you use, the energy price. Yeah.
Thank you. So thank you for the answer. So thank you. So I would like to move into Dr. Aziana for the question from the chat box. So there's a lot. So I have to just. So the first question is from Reza Hasim Zakariansyah again. So in the global race to decarbonize, hydrogen is often framed as the fuel of the future. Yet one of the least discussed but most decisive bottleneck lies not just in the efficiency of the electrolyzer and fuel cells, but in the accuracy of impedance-based diagnostic that determine their real-time performance and long-term durability. In this context, how do you see ALDAS and the advanced impedance measurement reshaping the narrative from simply producing hydrogen to actually building predictive, self-healing, and failure-resistant hydrogen system that could redefine cost-effectiveness and reliability benchmark for clean energy adoption? So that's the question, quite long. So the point is that he wants to ask, of course, hydrogen is fuel of the future, but actually, but bottleneck is not just lies on the efficiency of the electrolyzer and fuel cell, but also in the accuracy of this impedance, how we can determine the real-time performance and long-term durability of the cells for this energy conversion device. So, and how do you see your system, ALDAS, as the advanced impedance measurement can help to solve these problems.
Okay, thank you for summarizing the question. Basically, Hioki is an electrical measuring instrument company. We focus on the electrical part of the electrolyzer. Electrolyzer basically more on the chemistry side. Now, when you want to make a bigger scale, this chemistry based world will have to confront the electric side of the world. So there's a bottleneck, obviously, because there's two different like clashes of chemistry and electrical people. Of course, it is a lot of problems, but now we are trying to bridge this with our technology, because we do have technology for high current, high voltage. We have all this, system, but we never actually go through the chemistry side. Now the chemistry, of course, the hydrogen as a molecule is chemistry based, electrochemistry. So that's how we bridge it. We solve the part where the chemistry can't solve, the electrical part. So when you have this bridge created, you can build the predictive self-healing or failure-resistant system. But it's not just us, it's everyone. We provide you the tool. We provide you to how do you see this information that you can't see, that you're never able to measure. We provide you the system to measure them. And it is the researcher part where you need to learn what does each of these signal or what this data means. So that is how our basically our how to say our stance. I mean our part. So yes, that would be my answer.
Thank you. So actually, I have also question for your system. So regarding your system, because you said that you can use for multi-channels and also for the large scale, for kilowatts of the cell. So is it we need another booster to use your system?
No, you do not need anything.
Okay.
You can imagine like you have your own system and you just put a measure from outside. You don't actually intervene into the system of you already have the electrolyzer system. So you just plug and play. Like you don't need to do anything. Just you need some point where you have to connect the wires and everything. But that is just very minimal. You don't need to change the whole system, no need booster, you just use whatever you have. Yes.
So, there's some sort of question on the impedance spectra. So of course, for example, so to analyze the impedance spectra, sometimes we need advanced analysis methods as distribution of relaxation times. So that in your software, so it's possible to analyze to use the DRT. Yeah.
Yeah, I
to analyze the impedance
understand.
spectra.
Yeah, thank you for the question. I think this question is very good because
Mm.
obviously when you get a data, how you try to understand it. Of course, you use a lot of software tools like DRT, chromoscopic tests, and there's a lot of various of other tests that basically what these other tests is secondary. What we do is the primary. We measure something that is physical, which we measure it directly. We translate the world that we can't see in real time. And you talk about DRT and all this software is what you do after you get the information from the real world data. So they are actually analysis of the impedance data that we get from the measuring system. That's why, because the EIS measurement is not really stable because it's dynamic. It's very hard to measure. That's why it's very expensive as well. And it's not commonly used. But it is very useful because you can know a lot of things from this measurement. So that's why from previously they use a lot of potential stat and everything. You will get very various kind of results. How do you want to make sense of the result? How do you want to build the equivalent circuit that match the physical quantity with the impedance data that you have is through course, the DRT and all those software. But that is a secondary. For our company, we do not have, inbuilt the ALDAS measurement for the one that we use for measurement does not include this analysis software, but you can use the other software with our data, because our data is just the normal from Excel file. You can just export it to ZView. We can also save in ZView, where you can do more analysis in detail about this impedance spectra. But for ALDAS, it's like a communication tool with something that you can't see. So we translate this invisible data to a visible data, where you can use the data, and then you can do a lot of various evaluation or analysis. So the answer is we don't have them inbuilt in the in our software. It's just for measurement and the setting for the measurement system. So mostly measurement, purely measurement. And of course we can see those graph, but further than that, we need another software. Yeah.
Thank you. So we have another question. So Yuda Prima Hardianto. So you raise your hand. So if you have question, please ask the question to the presenter, please.
Okay, thank you so much, Dr. Ian, for a very nice introduction. So basically, Assalamualaikum warahmatullahi wabarakatuh. Thank you so much, Dr. Aziana and also Dr. Shahbuddin for very nice presentation, and it is very insightful talk. And by the way, I really appreciate what you presented previously. So, actually, I'm following the question from Dr. Ian. So, regarding the booster for the potential start, I think, the ALDAS here I can consider as a kind of potential start, right? So that's why, the booster for us is very important because if we want to scale up, if we want to make a large scale of the system, so we need to have a higher current. So that's why actually sometimes the booster is required. So whether the others can be custom by booster or not, that is my question, my first question. And the second question, actually, when we are performing the EIS normally, so we are applying the potential because we have to be really accurate to be to set our initial potential at so-called OCP or open circuit potential. So but when I hear your presentations about the ALDAS, so it give a parameter of current. So is this ALDAS can also provide set the current instead set the potential instead of current. So that's why the ALDAS can be used for double parameter, either current or potential. So that is my second question. Thank you so much. Assalamualaikum.
Okay, thank you for the question. So please, Dr. Aziana.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for your question. I just want to clarify that ALDAS is not a potential start. Potential start, ALDAS is actually doing something that potential start can do, but we are not potential start. Potential start, as the name is potential, it's a potential, right? The voltage. And I agree that you need booster for potential start, but you don't need booster for ALDAS. Why? Because your system already supplied the DC current. We are not supplying DC current. We do measurement. Like, for example, your multimeter doesn't supply current to your system. They just measure the voltage, measure the current, the clamp the current, right? So for ALDAS, it's not potential start. We use AC current. I'm not sure what potential start are you using. If, for instance, Biologic, they have two types of how you can measure EIS. One is GEIS, and another one is PEIS by potential. One is by galvanostatic. We are more on the GEIS, where we use the current for the signal to apply the signal for the measurement signal. And also we also do not use potential. We only use the current as a measurement signal. we don't have the potential for the current signal for the current product that we have, the Aldas Mini. It's based on that. And also we don't have booster because it is obviously it is externally it's supported. It's not supplying anything. They just more like electronic load, and it is specifically for electrolysis cell. So fuel cell have a different kind of operation. So the Aldas Mini, the one that we've launched is based on electrolyzers. So we use something like electronic load. So we don't need booster because I think in your laboratory probably you don't have the external DC power supply. So that's why you use booster to get the EIS. But then if your system already have your own DC power supply, you can use whatever DC supply in the market. If it's better version is this will be get nicer graph, but then any DC power supply will do connected to your electrolyzer, and you just connect the plug and play. No booster is needed. And we claim we can measure high current because Hyoki have this what do you call it, current sensor technology that was established to be very non-invasive. It's just clamp and it has very high accuracy, and that's what helps us to actually bring this up to another level to measure the higher current range for electrolyzer fuel cell. Yes, I hope I answered your question. Is it okay?
Okay, thank you so much. But basically, is there any limit of the current you can apply in the Aldas?
Obviously there is a limitation for the smaller Aldas Mini and Aldas E. They have different current limitation based on the specification, but 500 ampere for
okay. It's quite high. It's very high.
So it's
Yeah,
not
yeah,
for
yeah.
like lab. If you want to use for the small scale 1 by 1 centimeter square, I don't recommend Aldas Mini
Yeah, yeah,
because
yeah.
it's very small scale. If you want to go bigger, larger scale, then probably can consider use Aldas for active line measurement. Thank you very much.
Okay, thank you so much, Dr. Rajana, for the very nice explanation. Thank you.
Thank you for Dr. Rajana for the answer. So we have one more question. Is that okay for Dr. Shahabuddin?
Okay.
Sorry. So thank you for Dr. Rajana for that answer. So we will have one more question from the chat box. So the question we choose from Handi Sumarta Gunawan. The question is, considering the constraint of critical raw materials, energy price volatility, and cross-sector integration, power to X, how do you envision the role of low-temperature electrolyzer within the resilient and decentralized energy architecture across ASEAN? That's the question. So the question is, what kind of role of low-temperature electrolyzer within the resilience and decentralized energy architecture across Southeast Asian?
Okay. So the question is on the low temperature for the resilience and decentralized, right?
Yes.
Okay.
Yes.
Yeah. So yeah, of course, decentralized. So basically that one depends, as I mentioned before. So that one depends on the what kind of the energy resources that you have. For example, you can develop for example, the solar farms for small solar farms, or maybe you can have a mini hydro. So once you have the mini hydro or mini solar farms, then of course you can use, but in terms of the capacity is very small, quite small. So because the mini hydro maybe can up to maybe only 10 kilowatts, and solar farms, it depends on the site, depends on the area. So then of course you can have to do that in terms of the decentralized. And of course the decentralized, of course, it is good for a certain rural area, for example. For example, in the small village, okay, and industry parks or the island parks. So you can install it, for example, the island maybe wind, if you have a strong wind, and solar farms if you have very good in terms of the space area and so on. And in terms of the ASEAN energy system, basically, ASEAN actually the climate's almost similar. Then of course you can have solar and wind and also the hydro as renewable energy resources using for the electrolyzer and to produce the hydrogens. I think that's all for me.
Okay, thank you for the answer. So we still have time for the discussion session. Still have time. Okay. So I have to choose one question again from the chat box. So the question is for there's a lot of questions, so I have to choose.
Please choose one.
So the question from Zulfi QC University. So the question is, as you mentioned in your, this is for Dr. Shahuddin. So as you mentioned in your slides, the cost reduction of water electrolyzer technology requires improvement of the component performance. In UKM, in your university, which component are being improved or what sort of research topic are currently ongoing? And why do you focus specifically on those components? Thank you very much. So the question is...
The second question is what? Pardon?
The second question is, why do you focus specifically on those components?
Okay, thank you. So so in terms of the R&D in KM for the electrolyzer, basically currently we are focusing on the two types of electrolyzer. Basically for the anion exchange membrane electrolyzer, still on the polymer electrolyte membrane, but the anion side using the low concentrations of the alkaline. And also we also concentrating on the PEM electrolyzer. So based on these two types of electrolyzer, so the components that we are focusing basically on the catalyst side. So the catalyst similarly trend basically we still use the common conventional catalyst, for example, iridiums and platinum, but we try to reduce the loading at the electrode side. Okay, and also we developed a new synthesized catalyst, for example, for the AM electrolyzer. So we try to develop bifunctional catalyst, which is the catalyst can use in both anode and cathode to produce the hydrogen to break the water. This is the catalyst is basically on the nickel-based catalyst, either binary or ternary alloy metals. So and also we work on the bipolar plate basically. So the bipolar plates basically we try to improve in terms of the design. Okay, the profile channels, how the returns will be fluid equally in the bipolar plates. So we try to develop that kind of bipolar plates using a different design, and also we try to reduce in terms of the manufacturing costs. So basically there's a lot of manufacturing technology. Then we try to reduce in terms of the cost, one on the fabrications, and the ones in terms of the materials. So we try to find a good materials, a cheap materials to do or to develop the bipolar plates. And also that one is on the bipolar plate, and we also do research on the coating bipolar plate, because we need to prevent the bipolar plate tend to corrosive. So we need to prevent by using the coating. So we have a certain we try to develop the process And also we try to use a different materials as a coating material for the bipolar plates. Okay. And the part maybe on the system, we try to design the good system configurations purposely to reduce in terms of the power consumptions. By doing that, maybe we can have a very good, very high efficiency of the electrolyzer system, as well as to reduce the cost of the efficiency. And so why of course, as I mentioned, the material is very related to the capex. So basically, the capex, as I mentioned before in the slides, so there is a certain part basically that we need to emphasize, basically on the electrode and also the bipolar plate, because these two major components will be contribute much on the stack level cost, right? So that's why we try to reduce the cost in these two materials, bipolar plates and also the catalyst. Okay, I hope I answered the questions.
Thank you for the question. So also I have a question for you. So if you reduce the platinum or any metal, precious metal in your catalyst, so it will have some, what I can say, so the performance is not so good if we had more precious metal. So how do you make to solve this problem? So
So basically, yeah, of course, once we reduce in terms of the conventional catalyst, platinum iridium, so we need to add another metals. So then we try to do the optimization for a proper formulation for those metals. For example, we try to use iron and so on. Yeah, so this is the way how we try to reduce in terms of the cost by using another metals or combine with the conventional metals. Yeah.
So what kind of metal like happening in the research? So what kind of metal we can use to replace PT iridium?
So depends on the types of electrolyzer. IEM basically, they of course nickel-based catalysts, but plus cobalt, iron, and as well the iridium we use maybe ruthenium sometimes. So then those formula, the metal composition is quite important to have a very good electrochemical reactions and the performance in it. So we need to formulate and optimize those kind of the materials instead of just use the iridium oxide, for example, for the pen, and also the platinums at the cathode side.
Thank you. So I have a question again for from Dr. Aziana. So we have a question from, I think some question is quite similar. So this one quite interesting question. So can ALDA software be used to check for leaks in hydrogen generator? If so, to what extent it can be used to analyze leak to minimize risk to operator? Do you think it can be used to check leak in hydrogen generator?
Thank you for the question. The answer is no. Because
Yes.
the leak generates
Okay.
the leak is the gas. The gas needs some sort of gas meter. The ALDAS is the electrical part. Of course, hydrogen is generated, but the hydrogen will go to another sort of system. What ALDAS is do is the electrical part, because anything that is connected to electricity, and you have a DC current, you have the DUT, you have voltage, you have current, we can measure. So that's the very simple concept of ALDAS. So if you talk about leak, it will go for like gas meter, or there's a different part. So it's not electrical part. So the answer will be no. Yeah.
Yes. The answer is no, of course. So do we still have time for discussion? Stuff? I think it's enough for the discussion today. So I would like to thank Dr. Shahbuddin and also Dr. Aziana for today's presentation, and also it's quite very interesting talk you give us today. And I will I hope we can see you again in the future. So thank you very much, and also thank you for your discussion. Thank you. So I will return to MC for today. Thank you.
Terima kasih, Dr. Rian. Baik, demikian tadi telah kita simak bersama sesi utama kita pada webinar kali ini, yaitu sesi presentasi dan diskusi atau tanya jawab. Terima kasih kami sampaikan kepada Dr. Rian selaku moderator, serta para narasumber, Dr. Shahbuddin dan Dr. Aziana atas materi dan diskusi yang sangat bermanfaat. Thank you for all speakers for sharing their valuable knowledge with us today. Dan terima kasih juga kepada seluruh peserta yang telah berpartisipasi aktif dalam acara ini. Sepertinya cukup banyak pertanyaan gitu ya yang diajukan oleh para peserta, namun kami mohon maaf karena keterbatasan waktu tidak bisa untuk kami bacakan dan untuk dijawab semua. Sekali lagi kami ucapkan terima kasih atas antusiasnya. Kami ingatkan kembali bagi Bapak Ibu dan seluruh peserta webinar yang belum mengisi daftar hadir, agar dapat mengisi daftar hadir yang telah kami share di kolom chat. Terima kasih.
Permisi Mbak, dari tadi
Ya.
banyak pertanyaan, apakah materinya akan dikirimkan by email atau
Untuk
tidak, tapi belum ada yang menjawab.
nanti akan kami informasikan kembali Pak. Untuk informasi, rekaman webinar kali ini akan kami unggah di YouTube IFHE Official. Nanti mungkin bisa disimak melalui channel YouTube tersebut mungkin ya Pak.
Iya, baik.
Ya,
Terima kasih untuk informasinya.
ya, terima kasih. Nanti untuk kami perlu konfirmasikan kembali kepada para narasumber apakah bisa di-share atau tidak begitu. Baik, terima kasih. Baik, Bapak, Ibu, dan hadirin sekalian, selanjutnya kita memasuki acara penyerahan sertifikat secara simbolis kepada narasumber. Sertifikat pertama diberikan kepada pembicara pertama, yaitu Associate Professor Dr. Muhammad Shahbuddin Master dari University Kebangsaan Malaysia. Terima kasih atas sharing knowledge-nya. Thank you, Dr. Shahbuddin. Selanjutnya, sertifikat kedua diberikan kepada Dr. Noraziana Alita dari Hyoki Corporation. Thank you very much, Dr. Aziana, for the insightful presentation and contribution to this webinar. Dan terakhir, sertifikat untuk Dr. Rian Ahmad Budiman selaku moderator. Terima kasih telah berkenan memandu acara di sesi utama webinar hari ini. Kita berikan tepuk tangan yang meriah untuk para narasumber kita dan juga moderator pada hari ini. Baik Bapak Ibu, demikian tadi sesi penyerahan sertifikat. Semoga acara pada hari ini dapat memberikan manfaat untuk kita semua. Selanjutnya, Bapak Ibu dan hadirin yang kami hormati, tibalah saat yang ditunggu-tunggu mungkin, yaitu pengumuman pemenang door prize. Door prize akan diberikan kepada 3 orang penanya dengan pertanyaan terbaik. Untuk itu, kami umumkan pemenang door prize pada hari ini. Yang pertama adalah Bapak Reza Hashim Zakariansyah, Esos dari Airlangga University. Apakah masih hadir bersama kita di siang hari ini? Kemudian yang kedua,
Ya, hadir. Terima
baik.
kasih.
Kemudian yang kedua, Ibu Tridila Usma dari Syah Kuala University. Dan yang ketiga, Bapak Zulfi dari Kyushu University. Selamat kami ucapkan kepada para pemenang. Apakah ketiga pemenang kita masih ada bersama kita? Mohon untuk dapat di spotlight dan mungkin bisa memberikan sedikit kesan dan pesannya begitu ya ketika mengikuti acara webinar hari ini, dan juga mungkin bisa sedikit memberikan masukan untuk topik webinar kita ke depan.
Oke,
Mungkin yang
ya,
pertama
baik,
dari ya, Bapak Reza, silakan.
baik, ya, terima kasih Mbak. Saya akan coba sampaikan dalam bahasa Indonesia aja agar
Ya,
lebih mudah
silakan,
dan
monggo.
oke.
Ya, silakan.
Baik, ya, webinar hari ini ya berlangsung dengan sangat baik ya, terutama kita akan membahas tentang bagaimana energi hijau baru dan terbarukan ini begitu sangat penting karena kedepannya ini kan penggunaan fosil itu kan lama-kelamaan akan semakin berkurang bahkan habis ya dalam masa waktu tertentu. Jadi ya pentingnya bagi kita terutama saya ya generasi muda mahasiswa yang sedang menempuh S2 juga ini agar semakin tergugah kesadarannya terkait dengan penggunaan energi baru terbarukan. Saya juga mengucapkan terima kasih kepada para penyelenggara, para tim yang ada di balik layar ini juga ya, termasuk para narasumber kita yang berasal dari negara Malaysia. Ya, sekali lagi terima kasih banyak.
Baik, terima kasih. Selanjutnya mungkin pemenang berikutnya. Jika ada pesan dan kesan atau masukan yang ingin disampaikan untuk webinar kita selanjutnya. Sudah ya? Sepertinya yang lain sudah meninggalkan Zoom meeting ya. Untuk konfirmasi pengiriman hadiah, kami mohon kepada para pemenang door prize nanti agar dapat menghubungi panitia via WhatsApp, email, ataupun DM Instagram yang telah kami cantumkan pada flyer webinar. Atau mohon dipastikan telah mengisi daftar hadir dengan data yang lengkap agar dapat dihubungi oleh panitia. Terima kasih. Dan sekali lagi kami ingatkan kepada Bapak Ibu, kami ingatkan kembali bagi yang belum mengisi daftar hadir, agar dapat mengisi daftar hadir yang telah di-share di kolom chat. Oke. Baik, Bapak Ibu dan hadirin sekalian, demikianlah seluruh rangkaian acara e-Talks ke-14, Webinar Series on Clean Energy and Advanced Materials, telah kita lalui, sampailah kita di penghujung acara, yaitu penutup. Atas nama panitia yang bertugas, kami mengucapkan terima kasih kepada seluruh narasumber, moderator, dan seluruh peserta yang telah hadir dan berpartisipasi aktif. Kami ucapkan terima kasih juga kepada para sponsor, PT Hyoki Electric Instrument, PT ITS Science Indonesia, dan juga PT PLN Nusadaya atas dukungannya. Webinar ini juga disiarkan secara langsung melalui kanal YouTube IFHE Official dan dapat Bapak Ibu simak kembali. Semoga kegiatan hari ini bermanfaat bagi kita semua, dan kami mohon maaf jika ada kekurangan dalam penyelenggaraan acara ini. Sampai jumpa pada kegiatan IFHE berikutnya. Yang terdekat, webinar series pada tanggal 21 Oktober 2025. Kemudian akan ada Hydrogen Day dan IFHE juga akan mengadakan event besar, yaitu Global Hydrogen Ecosystem Summit atau GHS pada tahun 2026. Baik, Bapak Ibu, kita tutup acara ini. Sedikit pantun penutup. Naik sepeda ke kota tua, sehingga sebentar membeli jamu.
Cakep.
Webinar kita telah selesai semua. Terima kasih, sehat dan sukses selalu. Selamat siang. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.